Series solutions of ordinary differential equations. 60 years ago in my first ODE class, which I took out of Rainville's ODE book, was just nothing but solution techniques. The course has changed in recent days. You got topics like dynamical systems, modeling. But my recollection back working out of Rainville's book on the topic of series solutions for this differential equation: linear, second order, homogeneous or inhomogeneous. A lot of tedious manipulations on series. Some turn out to be Taylor series, some turn out to be more generalized series. And I kept looking over the years for Maple tools that would implement some of those manipulations, but in a more user-friendly way than you do by hand. Now, you can get series solutions out of Maple. It will give you the series whenever it knows what that series is. But what about tools for deriving a series from first principles? So this presentation summarizes what I've learned in Maple and found in Maple that would have been of great use to my younger self back in the days when I was an undergraduate, trying to do some of that Rainville-inspired math that I mastered so many years ago. So suppose you wanted to get a solution in a series expanded about point x naught. Well, that point would be called a regular point for such a differential equation if the solution turns out to be power series. And when will that happen? If the coefficients a, b, c, and f are analytic at that point, and this leading coefficient does not vanish at that point, you could divide by a of x, and then you'll see that you have three analytic functions. Y double prime equals that. By repeated differentiation of this differential equation in this form, you can compute higher and higher derivatives, and therefore you can obtain the solution. That makes a x naught a regular point. How about an example to illustrate what we're talking about? Take a simple differential equation, constant coefficients, inert initial conditions, something that we can get an exact solution to. And therefore, since this is the exact solution, we can expand it in a Taylor series, and we can see what the series solution looks like before we get started. Now, in table 1, what I've done is I've used the differential equation to compute these coefficients. So we know y at 0 and y prime at 0. How about y double prime at 0? So this is 0, this is 0, e to the 0 is 1. That's what these numbers are. So that coefficient is 1, and the A2 coefficient in the expansion is going to be 1 over 2 factorial. To get A3, the next coefficient, differentiate this equation. So this is the derivative. We know y prime. We've just computed y double prime. This is the derivative of f evaluated at x equals 0. These are the numbers. Comes out to be -5. So you divide by 3 factorial, and that coefficient is -5/6. One more of these here. You differentiate again, y fourth, derivative here, second derivative, third derivative. We've just evaluated that third derivative, so we know that. We evaluated before and got the second derivative. Here are the numbers that you're going to be playing with. It turns out to be 8. Divide by 4 factorial. that coefficient is 1/3. That's how you can generate the series. If it's a Taylor series, at x0, which is therefore a regular point. Table 2, right here, captures these computations in some Maple code. You can see we've generated -5 to 8 to 32. This is the differential equation. We're going to differentiate it here, evaluating it at 0 here. As you generate these numbers, give them some placeholders. I use D as the placeholders, so then you have the previous values that you've computed. You do an evaluation of the expression. That's the putting in over here, and then I've just printed them out. So here's a table that you can experiment with to generate the coefficients of a Taylor expansion from the differential equation. So let's move on to example 2. Example 2, we illustrate the traditional by hands technique for generating that Taylor series expansion. Same differential equation, same initial conditions. So what you do is you assume a solution of the form shown here. It's a Taylor expansion. Plug that into the differential equation. But this e to the minus x on the right has to be itself expanded in the Taylor series. So look at what happens here. Second derivative of this term, you get n minus 1, x to the n minus 2. And notice I've started that series with n equals 2 because when n equals 0 and then n equals 1, there's nothing there. You get zeros. So you might as well start that sum from 2. Here you have the first derivative. You get n x to the n minus 1. And when n is 0, nothing there. So you start this series at n equals 1. No change here. And here's the series for e to the minus x. So look at the terms that you have. This term, x to the n minus 2. This term, x to the n minus 1. This term, x to the n. This term, x to the n. And what you want to do is you want to get all of these terms to read x to the n. So you got some series manipulations to do. Suppose you look at this n minus 2, and you say, I would like that to be the letter k, which means that n must be changed to k plus 2, so that when n is 2, k will be 0. So this term becomes, here you have an n, it becomes k plus 2. This term will become a k plus 1. This an will be a k plus 2. And this will read x to the k. And k will start at 0. Here you want n minus 1 to read k. So n is, in this sum, k plus 1. When n is 1, k is 0. And so this sum, that n becomes a k plus 1. This a sub n becomes a sub k plus 1. The x becomes an x to the k. And this series, instead of starting at 1, will start at 0. No change here, no change here, except let's just change these n's to k's, so everything will be k. Now you can sum from 0 all of these 4 terms down here, factoring out the common x to the k. Each of these coefficients itself has to be 0, identically 0 for each value of k. The initial conditions, they're inert. They tell you that a0 and a1 will be 0. And so this equation, or this coefficient z equal to 0, will tell you what the succeeding coefficients are. So down here in table 3, what we've done is we have set this coefficient equal to 0 and solved for a k plus 2. And AK plus 2 is some multiple of the two previous AK plus 1 and AK. This is called the recursion formula. We know A0 and we know A1. So A2 can be computed, and it's a half. Now that we know A2, A3 can be computed, minus 5/6, etc. Notice that these numbers are going to be the same as the numbers that we got in the previous example when we used the differential equation directly to get the coefficients. And these are the manipulations that one would have learned 60 years ago reading or working out of a textbook like Rainville. So now in example 3, I want to see what tools Maple begins to provide us. So in table 4 here, take a look at some of these tools. Same differential equation. We need the right-hand side as a power series. So there's a way to do that. Convert to a formal power series e to the minus x. So this is now in a form where this command can work. There's this package series, linear ordinary differential equation. I think that's what that S stands for. It has a command FP series, formal power series, for this equation. The equation is in Y. V will be used for the coefficients. So you get this thing called a formal power series structure. These are the two coefficients that you've got to drop off, pull out of the sum. This sum starts at n equals 2. This is essentially the recursion equation. I'm going to grab it. That's what this command does. I grab it, and I would like it to look like the work that we did earlier where we used k. So I'm going to set this n equal to k plus 2. So I get this expression, and I isolate the vk plus 2 term. This should be the same as our previous recursion. The denominator here can be factored, so let's do that factoring, and let's write this in terms of A, and it compares to what we obtained previously. So there's a tool that Maple provides that helps us get a series solution in closed form. Now, it turns out that this particular recursion can be solved in Maple. So here is the recursion solve command being applied. The answer comes back. It's kind of messy, so we clean it up a bit. And this expression will give you the terms of this recursion. So here's a sequence of some of them, and they match what we've obtained in the two previous examples. So here is one tool that Maple has along the line of finding series solutions from closer to fundamental principles. So we've looked at regular points where the coefficients stay analytic. If they're not analytic, then you're talking about singular points. And singular points come in two varieties. So a point that is not regular is called singular, but singular comes in two varieties. And you have the nomenclature regular point, which is what we just looked at. Then you have a regular singular point, and then irregular singular point. It's not the most straightforward terminology, but that's what we're stuck with. Okay, and what we are going to look at is the regular singular point. They are singular points that aren't so bad. The irregular singular points, the solutions behave very strangely, and we're not going to look at that. We're just going to look at this regular singular point. Regular singular point for this differential equation, notice that the leading coefficient here is 1. You have P and a Q, and it's homogeneous equation. We put limits on how bad the singularities in P and Q are. If there were no singularities in P and Q, it would be a regular point. But if there is, if they're not analytic functions, they are going to have some kind of bad behavior. We put a limit on that bad behavior. P has a pole of order 1 at worst. Q has a pole of order 2 at worst. So P will look something like this. There'll be a leading coefficient of the Laurent expansion, and Q will look like this. There will be two leading terms in the Laurent expansion. Now, from these coefficients, P sub minus 1, Q minus 2, Q minus 1, we can write down this quadratic equation. It's called the indicial equation. The coefficients P minus 1 and Q minus 2 appear. We will soon see where this equation comes from. But this equation has two roots. We'll call those roots alpha, beta, and we'll order them so that the real part of beta is greater than or equal to the real part of alpha. That will then determine the nature of the solutions at this regular singular point. And this stuff is what's called the Frobenius theory. One solution will be a generalized power series. It will have x to the beta out front, and this part will be a regular Taylor series. There may be a second solution of a similar form with x to the alpha out front of what looks like a Taylor series. But there may be a second solution, not of the form y2, but of this form, y1 times a log plus another series of the form x to the alpha Taylor. And this are not the same. So when do you get these different solutions? Well, there's always a solution of the form y1. If alpha and beta are the same, if it's a repeated root, guaranteed you're going to get this third solution, y3. We'll have a log in it. If beta and alpha differ by a positive integer, this second solution, or the second solution, may be y2 or it may be y3. You don't know. Now, this is getting complicated. We definitely need an example. So here's an example, and notice it's got 5 parts to it. So this example has as its leading coefficient an x squared. So things are not going to be analytic at 0. Let's divide through by that 2x squared, and we see this would be P, and this would be Q, and just the Laurent part is there. So P sub minus 1 is this 3/2, and Q minus 2 is this negative 1/2, the piece over the x squared term. So we write the indicial equation, and we see there are two roots. They're distinct. One is a half, one is minus 1. They do not differ by an integer. Therefore, the solutions are of the form y1 and y2. We're going to get two of these generalized power series. We can deal with them at the same time by writing one solution, a test template, in the form of x to the n plus r, where R will be either alpha or beta. So if we take that and punch it into the differential equation, we're going to get, for two derivatives, we're going to get n plus r minus 1, x to the n plus r minus 2. The first derivative term will be n plus r, x to the n plus r minus 1, and the no derivative term will look like that. So because some of these multipliers are themselves binomials, when you multiply all these out, you're going to get 5 different series to deal with. And I've color-coded them. The yellow ones have x to the n plus r. The orange ones, or pumpkin color ones, have x to the n plus r plus 1. And the reason why you get either n plus r or n plus r plus 1 is you got these multipliers out front. 2x squared, you'd like to get that x squared joined up over here, so you get an n plus r. And here you have an x squared. You would like to push that x squared in here, and the minus 1 becomes a plus 1. Here you have a 3x, so you have only a single x multiplying. You push that inside, and this then becomes an n plus r. Here you have an x, so you're going to go to an n plus r plus 1. This is a constant. You're going to get an n plus r. So you have these two different kinds of series. One that has n plus r and one that is n plus r plus 1. So here in table 7, I have put those terms that have x to the n plus r on the left, and those are terms that have x to the n plus r plus 1 on the right. I have factored the coefficients of whatever you have here with n plus r, and I've done the same with n plus r plus 1. And so there's a process now of collapsing stuff, factoring up a bit, and looking at this and saying, okay, this is of the form n plus r. I'm just going to let n become k, and k will start at 0. This is not too bad. I don't have to do too much over here. But n plus r plus 1, I would like that to read k plus r. So I have to shift n to k minus 1. And when n is 0, k will be 1. So this series will start at k equals 1. It will have x to the k plus r. And here I've cleaned up what the coefficient will look like. So here's sum from 0. Here's sum from 1. I cannot bring these two terms together yet. I have to pick off the k equals 0 term from this sum and start it at k equals 1 so I can join it to this series. That term, the k equals 0 term, is this. K equals 0, you're going to get an r. You're going to get a 2 times r plus 1. But there's a 2. There's a minus 1. This is what it looks like. This is the initial equation. And if you manipulate it, you'll see that it's the initial equation we solved earlier. This term tells you what this series will look like. This piece gives you the recursion. And it turns out that ck is a multiple of ck minus 1. Well, we have already determined the values of alpha and beta. So when r is the beta value, which is 1/2, this recursion becomes this. And I'll say bk in terms of bk minus 1. Does that make sense? We got r is a half, so you got a half here. You're going to get a 2k, you're going to get a 1 and a 1. So we get 2 factor of k plus 1. And you can check out that this becomes this when r is a half. When r is the other root, minus 1, I'll call that the a's. And we'll get ak in terms of ak minus 1. And this will become this recursion. In table 9, we have used these two recursions to generate coefficients. So b1 being a multiple of b0, you'll have this. Then b2, which is a multiple of b1, but b1 is a multiple of b0, you will have this. b3, which is a multiple of b2, but b2 we've expressed as a multiple of b0, so you'll have this. And similarly here in the other recursion, a1 is a multiple of a0, a2 is a multiple of a1, but a1 is a multiple of a0, you have this. And a3 is a multiple of a2, but a2 is a multiple of a0, so we have this. So with these two recursions, we are generating the coefficients of two series. And finally, in table 10, we put the two series together. X to the beta, that's x to the 1/2, so there's your root x, and then this is a Taylor series, and x to the alpha, that's x to the minus 1, so that's 1 over x. This is a Taylor series. Every term had a beta or a b0, and here every term had an a0. These are the two solutions, big Y1 and big Y2. So pretty much we've been using Maple as a typewriter at the moment. What are some of the Maple tools that we could use? Well, a relatively new component of Maple is the Student ODEs package. If you load it, then you can even access it from the context panel, and this would then be the chain that you'd go through. Student ODEs in the context panel. There's a solve. It opens to series solution, series y of x. So here's the differential equation, and if you do that, you will get this return. You get two series. They both start at 0, so this is the k minus 1, so when k is 0, you're going to get x to the minus 1. This is the alpha series. And here you have the 1/2. This is going to be the square root out front. It's the beta series. And in fact, you also get the two recursions. There are the two recursions, the A and the B. These recursions can be solved in closed form. Turns out that rsolve, Maple's rsolve command, recursion solve, will produce the general form for the AKs. And here is a sequence of the values you get. And if you add those times powers of x, you get this series. And you do the same thing here with the other recursion, the beta one, the B, and you see these values pop up. And if you add b times x to the k plus 1/2, you get this series with the square root. And if you do dsolve comma series, you get these two series, but they're truncated. You can get as many terms as you like, but they're truncated. You don't get a general form. You see these terms match down here, and these terms match down here. Now, surprisingly, this Student ODEs package has added stepwise solutions. So using the context panel, you can follow solve. This is the path, generic general solution with steps. click on this differential equation, and you get a stepwise solution, much like we have been going through by hand techniques displayed in Maple so far. However, in this solution that you can read at your leisure, you do not see Maple using Maple commands to get all of the manipulations that we had to go through. There are places in this stepwise solution where Maple just types out, do this, get that, or start with this, or change this to that. So far, we have not seen tools that would let us do precisely and exactly what we had to learn to do by hand out of Rainville's book 60 years ago. So let's see if we can find some Maple tools help us with this work. So here in table 11, I'm going to get Maple's desolve solution, and Maple can actually solve this equation exactly, closed form. I'm going to take a look at this power series solution, or not power series solution, the series solution that this command in the DE tools package generates. It's the same as Maple's desolve series, right? Desolve series, this and this, basically the same. Series. Here's the square root out front. Here's the 1 over x. I'm going to grab these two exact expressions in a unique fashion. That's what this code does. It grabs these two pieces in the same order every time. Then I get a series for each of them. And here's the one with the square root. So this is the one where the initial root beta is a half, and here alpha is -1. And if you compare the expansions of these two exact expressions to Maple's desolve series, they match. Now, so far, it's been all symbols. There's nothing visual here. So I said, let's pose an initial value problem and draw a graph. What does the solution look like? So I cannot impose an initial condition at x equals 0 because that's a singular point, and you can't compute the solution from the differential equation at such a singular point. That's what a singular point is all about. So I shifted over x equals 1/100th. And I arbitrarily picked y and y prime to have the values 1 and 2. This is what that solution looks like. So you get asymptotic behavior here near the singular point. Okay, that you can see something there. And then the rest of it, it behaves analytically, nicely. And in fact, if you take the limit of these two expressions, it goes to 0. So what additional tools might Maple provide? So here in table 12, we'll take a look at some of these tools. There is in the DE tools package this singularities command. It will tell us that 0 is a regular singular point. Now, it's not a regular point. It's a regular singular point. And infinity is an irregular singular point. There is an indicial equation command in the DE tools package. It will provide the indicial equation, and I've solved it, and we get the two roots we've seen before, 1/2 and -1. And let's try applying this command we've seen already, S series, linear ordinary differential equation, formal power series. We get a formal power series structure. We have this sum, and we have what turns out to be the recursion relation. look at that very carefully. There's something going on here. Let's grab it. Let's isolate Vn. It's given in terms of Vn minus 1. This is a recursion that can be solved. Let's generate some of the coefficients. Those numbers are the numbers we see in y2, the 1 over x. The initial root equals minus 1. Why not the one where the initial root was a half? Well, I guess it turns out that it can't provide that. So it's a tool that will provide you something, but it's not everything yet. So let's try using Maple directly to implement the steps of this Frobenius stuff. Here's the differential equation. Let's put in for y of x a sum of this form. That's going to then require some manipulations and simplifications. So I have found that I had to do this. I've tried many things. Expand, then evaluate. See, why am I expanding? Because you have a multiplier here and a multiplier here. Expand, then substitute. And we have this now to deal with. You have an x squared out front. We'd love to cancel that with this x squared. And we'd love to cancel that with this x. And you have the same thing happening here. X squared out front. You'd like to cancel with this x. This x and that x should cancel. How can you get Maple to do that? What Maple commands will let us do that stuff automatically? So what's the goal here? I would like these two terms to combine. The x squares, the numerator and denominator, cancel, and then clean up this stuff to this coefficient times an x to the n plus r. I would like this term to have this x, see x squared and x, change this x to an n plus r plus 1, n plus r plus 1. And I've colored that because there's going to be one other term like that. I'd like this term to have the x's cancel, and I have a just plain x to the n plus r. This term, 3 is out front, but there's a trailing x, and that would be an x to the n plus r plus 1, and there'd be no change here. That's what I'm trying to accomplish with these terms. Because if I could get that to happen, then I could shift index here and make this k plus r, but it would start at 1. And I could make this k plus r, but I would have to shift the index and it would start at 1. And if I could get that far, then I could pull out the k equals 0 term from this sum, and this sum. And you'll see I've done that separately here. I've pulled it out here, I've pulled it out here, and I've pulled it out here. Then the terms in x to the k plus r that all start at k equals 1 would be here, and I would have my initial equation from, not my initial equation, I'd have my recursion equation from here, and my initial equation from the pieces that I had to pull out. If I could do that, if I could manipulate these pieces the way I do with a pencil and paper, I would have it done in Maple. Now, I'm going to show you the best that I could come up with, that I personally could come up with. I call it a brutal technique. There are 5 chunks I've got to manipulate. So here are the names of the 5 chunks that I'm going to use. Let's just use TT1 through TT5. And I'm grabbing those 5 pieces that I want to manipulate, and I'm giving them these names. You can see in here, I have gone into those 5 pieces, and I have manipulated minutely pieces using the op command, which is a low-level command for ripping things out from the tree structure that holds these terms. And then I've used dechange command from PDE tools to shift indices and change the name of the index. So I'm using very, very, very low-level tools to do the manipulations that I learned out of Rainville by hand. Maple has not made this easier, has not provided tools for those manipulations. Having done those manipulations in this most brutal, painful way, in a way that I would never subject students to, I now have the 5 terms in a form where I can combine the appropriate series, take out the appropriate piece, get the recursion part and the indicial part, and here I have solved for CK in terms of CK minus 1, which gives me then 2 recursions. I get terms from those recursions because I R solve them, recursion solve them, which Maple can do, and then I get that expression, I get the terms, I do the same thing here, and we can see that we have gotten the terms from y1 and y2. Here you have the square root multiplying everything, and here you have the 1 over x multiplying everything. So if we could get past that stage of manipulating the series, then we have tools where we can get the pieces that we learned to do in Rainville's book 60 years ago. But this then is a stumbling block. Now remember what I said, that I personally did not manage to overcome that stumbling block. But I will give you a technique that is not mine, comes from this publication, Flight Manual, Maple, 1996. Here are the 3 fellows who wrote that: Wade Ellis, Eugene Johnson, 4 people, Ed Lodi, and Dan Schwalbe. It's a rather clever device for dealing with these series manipulations. Okay, so this technique will get us the recursion formula, but not the indicial equation. Here's the technique. Do not plug in a series from 0 to infinity. Since you're looking for a series that you can have x to the n plus r show up, sum on either side of x to the n plus r. So let n be k minus 2 to k plus 2. And you might have to massage those limits for a given differential equation. After plugging in, you do a simplify, and you'll notice that here is the term with x to the k plus r. These other terms of x to the k plus r minus 1, x to the k plus r minus 2, you don't want those. You want this term here. Because if you grab that which is what I did here. I said, give me the coefficient of the term that has x to the k plus r. That's what this thing does. And map, because this is set equal to 0, and the coefficient command only works on expressions, so you got to do each side separately. If you solve this for ck by using isolate, I get the ck on the left. This is the recursion that we wanted, did all those manipulations for, to get. There you have it. Okay? These two agree. A fifth and final example comes right out of the Rainville text that I used in undergraduate studies. Third edition, 1964. It's the second printing. This book is the second printing. The first printing is still called the third edition, and that's the one I use because I had graduated already in 64. I graduated in 63. Okay, here's the problem. Differential equation is a different one. Initial equation, initial roots repeated. So this is definitely the log solution case. Y1, you can see here, it's x to the k minus 1. So that's that 1 over x out front. The second solution is that times a logarithm plus another solution, another series that has a 1 over x out front of it. So now in table 14, I'm going to just give you a quick sketch of Rainville's solution to this problem. So he writes the template series, x to the r, ck, x to the k. Let us assume that this has been pushed through the differential equation, and ck has been determined as a function of r. So all of the work that you've seen in the previous 4 examples has been done, and the ck is given in terms of r. Rainville's first solution evaluates this expression at r equals minus 1. And he's pulled out the first term, and now the sum starts at 1. So you have this x, you have this sum from 1, and evaluate this at r equals minus 1. Put r equals minus 1 here. First solution. To get the second solution, the one with the logarithm in it, he does this. He differentiates with respect to r and evaluates at r equals minus 1. He does explain why this works, but this is the technique. And it's the differentiation with respect to r, and r is in the power, both here and here, is where the logarithm is coming from. And then you have the other term where you have to differentiate with respect to r because r is in the ck. I write that as ck dot, the dot meaning differentiate with respect to r. There's the second series. And here is the first series multiplied by the logarithm. So now in table 15, I summarize what took pages in Rainville's text. This is C as a function of R. When you differentiate with respect to R and evaluate it at minus 1, you see, because of this product down here, you're going to get repeated, you're going to get sums, and that's here. Okay? Now, Rainville introduces a symbol for the sum of the harmonic series up to index k. You could do that in Maple. Maple's got a function for that. Psi function. It wasn't necessary. I just left it as a sum. So his first solution is this, and his second solution is this. So let's see what Maple can do with this problem and what help it might be in implementing some of this material. Okay, differential equation, Desolve two solutions. They're Bessel functions. Bessel I, Bessel K, divided by x. And here's a graph. Here is the Bessel I over x, and here's the Bessel K over x. This one goes to 0. This one we're going to go up to infinity. Okay, so here in table 17, we're going to get Maple series solutions. Maple series solution, y1. This is the logarithmic one, so this is Maple series y3. And I want to compare to what Rainville got. This is Rainville's solution. I call it rho. If I type this into Maple this way and hit the Enter key, Maple sums that series and it becomes Bessel I over x. So I'm happy with that. If I take Maple's y1, which is the Bessel function, and convert it to a formal power series, I get this. And if I express this as a truncated series, I get these terms, which are these terms, which also appear here, just the way they're supposed to. Okay, so table 17 says the y1 solution, Rainville, Maple, they agree. I tried to do the same thing with the second solution, the logarithmic solution. This is the stuff Rainville produces. This is the stuff we reproduced in Maple, going one way, saying give me a series. But I looked at this graph. This is Maple's series for the second solution, for the logarithmic solution. And this is Maple when it says here's an exact solution. I was stumped by that for a while. Then I realized, wait a minute, this thing here, this is the psi function. Psi function minus the log of k in the limit becomes gamma. And when I did this, when I converted this exact solution to a truncated series, and I saw the gamma, then I realized what's happening. That accounts for the difference between these two graphs. So I was okay with that. So finally, can Maple reproduce Rainville's technique for obtaining the logarithmic solution? So let's take Rainville's CK of R. This is what it looks like. So this is then Rainville's general solution template. If you evaluated it -1, you get Bessel I over x. Let's truncate that. And we want to differentiate with respect to R. Let's see what happens if we do that derivative and evaluate at R equals -1. Lo and behold, we get the pieces that we have been seeing as both Maple's logarithmic solution series-wise and Rainville's terms. And here is a reminder of the gamma that showed up in table 18. So Maple does help understanding Rainville's technique for getting that logarithmic solution.